problem of segmented least squares, and we saw how there were more choices and so on. So today we'll look at this very famous problem actually two problems: subset sum and knapsack. And here we'll see that the obvious set of subproblems is not going to be enough. Okay, so today's sort of topic is what if the obvious set of subproblems is not enough. And we'll see what we mean by that. And then basically what we'll need to do is to define a richer set of or a larger set of subproblems. Okay. And so this is this is what we'll illustrate through these problems called subset sum and knapsack. But let's start first with subset sum. Okay. So again, we had these n requests in the resource allocation or scheduling problem, right? So suppose there are n requests again. One to n. And there is a single machine. And suppose each request comes with a wait, like kind of running time, let's say. That is Wi. And the machine can take a total wait. Capital W. Okay. And what do you want to do? Minimize the idle time for the machine. Select a subset of jobs such that together they minimize the idle time sort of, if the time is W is the time. Okay. For the machine. Right. So how will we formulate this now? So suppose we want a subset of jobs. So we want S subset of n such that. Okay. So can somebody define it for me? How will the definition look like? I mean, I've told the requirements. How do we say that formally now?
So to maximize the sum of all times individually, such that the sum of times does not exceed W.
Yes, this is what you're saying.
Yes, sir. This is what I'm saying.
Yeah, exactly, right. So Amit, you said, right? Yeah.
Yes, sir.
Yeah, good. So as Amit just said, that what are we trying to do? We are maximizing, this quantity, summation of Wi's which are in S. We want to find such a S such that, okay, I mean that maximizes, let's say, because this max here does not really is not syntactically correct. So maximizes Okay, this quantity, which is I in S, Wi, such that the summation is still less than W. Right? This is what we want to do. Is the problem definition clear? Any doubt about the problem definition? That we are given some times and we want to sum them up. We still want to keep them less than the total time which is there, but we don't want to like waste any capacity there. Okay. Good. So now how do we go about this, right? So let's see first what does greedy do. So there are two ways of greedy. First is pick smallest weight. Will this work? Or if it will not work, why?
Sir, it will not work.
Any counterexample, Amit, can you give?
Sir, let's say we have a maximum capacity of W, then this, and we have the set 1 comma W by 2 comma W by 2.
Okay. So you have 1 comma W by 2 comma W by 2, right? So here, if you pick the 1, then the maximum this number you can reach is W by 2 plus 1. And suppose W is like much larger than 2 is the, and while the optimum is W, right? And second strategy can be pick the largest weight. And in that case, what can be a counterexample? Somebody?
W by 2 plus 1 comma W by 2 comma W by 2.
Yeah, anything like, so let's say 2W by 3, W by 2, W by 2. And here also again, this is going to be what will be picked by the algorithm, and opt is going to be W. So these things don't work definitely. Greedy does not work. I mean, just for a sanity check, we check that okay, these are the two greedy strategies which don't work. Okay, good. So now let's try for DP, dynamic programming, right? Good. And as we had seen, there are three steps for greedy that will be defined. First was that find some polynomial number of subproblems. Right? And then easy to compute original optimum from subproblems, and an ordering and recurrence on the subproblems. Right? So this is what our strategy was, or this is what we want to do if we want to design a dynamic programming algorithm. Right? So these were the three basic fundamental building blocks. Okay, good. So now let's try to design an algorithm for this problem. Okay. So how, so again, let's argue we did for even for scheduling that okay, we pick one element, we try to argue okay, what happens when this element goes to the solution, what happens when this element does not go to the solution, and from there we try to get the recurrence, right? So again, let's let opt I denote the solution or the optimum solution or an optimum solution for the set 1 to I, right? Because this is what, these are going to be our, let's say, smaller subproblems, 1 to I for now, okay? So subproblems we are looking at is is like, let's whatever, like 1, 1, 2, so on, like, 1i, finally 1 to n. Right? So suppose these are the subproblems we are looking at. Okay, good. And the opt I solution to ith such subproblem is an optimum solution to ith such subproblem. Okay. Now look at an optimum solution O for 1 to n. So how were we arguing last time? That if n does not belong to O, then what can we say? Opt of n. Can we say something about opt of n?
That it will be same as opt of n minus 1.
Yes, it is going to be same as opt of n minus 1. Why? Because this guy now does, we know that it does not belong to the solution, the nth guy. So now whatever the optimum solution is, it has to be an optimum on this set. Because if it is not an optimum on this set, then you can look at the optimum on this set, whatever the optimum is of n minus 1, and then put that as a solution and get a better solution than whatever you have for opt. I mean, this is just, I mean, it does not really require a proof so much, but I'm just saying this for the sake of, that so that you understand that why this has to be opt n is equal to opt n minus 1. Okay, so in this case, when n is not part of the solution, then the optimum solution for the whole set has to be the optimum solution for the smaller set, which is of size n minus 1. Good. Now, but what if n is in the optimum solution, right? Then what did we have? In scheduling, we had that, okay, we could discard such things. But here, like, it's not very clear that what can we discard, right? And can we even relate it to, so, okay, fine. So again, opt n minus 1 is there, but can we relate it to that also? Right? And it's not like, so maybe we would want to write something like opt n is equal to whatever the weight of n plus, maybe opt n minus 1. But is this correct?
Uh, opt of n minus 1 need not have a weight less than equal to w minus wn.
Yes.
So
So,
basically, the sum would be greater than w.
yeah, weight can be more than w minus wn, right? This is what you said, Ayush?
Yes, sir.
Yeah, good. So now, if this is more than w minus wn, then if you sum it with wn, then total weight you get is more than w. So this does not work, right? So somehow, what do we want? We want to also incorporate, so we want the solution to the smaller subproblems. Let's say 1 to I, or which special case will be n minus 1, but also some capacity, small w, let's say, right? Because, and why do we want that? Because then that will give the solution for, let's say, 1 to n minus 1. I should have written it in the other way around, that we want this 1 to n minus 1 with capacity this much. with capacity W, capital W minus W, right? For example. Good. So this we want to find for some capacity. So this is now going to be our subproblem, right? So that what is left now? So somehow we want to have that information inside the problem definition, right? So now let's just so to know opt of n, we need to know opt n minus 1, let's say, and we also need to know opt of n minus 1, let's say, for capacity or for weight W minus WI. So this gives us, this, okay, I said the same thing actually, but just repeated only, but fine. Okay. So now what is the candidate for our, sub-problem, right? So sub-problem, let's say that now we'll have another variable in our sub-problem. So let's say opt I comma W, okay, denotes an optimum solution for one to I and total weight W. Okay. So now this is how our subproblem is going to look like. So now it has an additional variable. So this is now like a slightly richer set of subproblems than just defining the subproblems on the basis of 1 to I that as we had been doing before in the in other problems. Okay. So any question about the definition of the subproblem or anything? These subproblems. Yeah.
Solution means value or set.
Yes. So denotes an optimum solution. Yeah. Here. Okay. Let's say value of an optimum solution. Let's. Thank you for pointing out. Okay. So by value we want to have the. So what is value of a solution? So if S subset of n is a solution, then value of a solution is equal to that's what. Okay. Thank you. Okay, so right now we are considering the value, but again, as we had figured out before, if we can find a recurrence for the value, we can also recover the optimum solution from there, and we'll not worry about that too much. But I'll just write a line to tell you how will that be obtained. That is not going to be very hard. Any other question? Okay. So if not, then now let's see that how this subproblem will help us. So let's again try to argue about the n case, right? So consider the request n. Right. So again, if n is in O, then if n is not in O, then we already had this recurrence, right? That opt of n again now, but this is going to be W because now we have the full capacity is equal to opt of n minus 1 comma W, right? Because n is not in the solution, and if n is in the solution, then what is the thing we are going to get? opt of n comma w is equal to
wn plus opt of n minus 1 comma w minus w1.
yeah, sorry. wn plus opt of n minus 1 comma w minus w, right? So this is what we have for n, and basically, so now, so we have found that okay, how to find the solution of the larger subproblems, or the final subproblem using the smaller subproblems, and in fact, the final subproblem is actually a smaller subproblem. So opt n comma w is the solution, is the output. But now let's write a recurrence using similar thing, right? So now for take a general subproblem. One to I with capacity, let's say, or weight W, right? That is I comma W, right? So now I want to write something about opt of. So write recurrence for opt of I comma W. Right? Good. So now what is it that, so first we have to look at something that if this I itself is greater than W, the weight of the request I itself is greater than W, then what happens? So let's say if Wi is greater than W, then opt of I comma W is what? Then I cannot be
I
in W.
minus I
Yeah,
minus 1 comma w.
I minus 1 comma W, right? Why? Because in that case, this I cannot be part of the solution, right? So in that case, we don't even need to take the max with the other thing, right? Otherwise, we get similar recurrences, right? That if, okay, let's write it down just in detail because I think we have some time. So otherwise, we have that if Wi belongs to opt of, let's say, I comma W, then what is the recurrence we get? That opt of I comma W, or let's say does not belong, just like previously, right? Opt of I minus 1 comma W, right? And if Wi belongs to opt of I comma W, then we get opt of I comma W is equal to opt of, what is going to be here?
I minus 1 comma w minus wi plus wi.
Yes, plus W. Good. So now from these two, now we can write that. So these two are exhaustive cases. So now we can write the recurrence for opt of I comma W. So opt of I comma W. Just combine these two basically because these two are exhaustive cases. So just take the max of these two quantities. So max of opt of I minus 1 comma W comma Wi plus opt of I minus 1 comma W minus W. So this is the recurrence that we get. And this is the recurrence that we get if this Wi is not greater than W, right? Good. So now this basically tells us how to compute the uh, the smaller subproblems and so on. But what is the ordering here? What is the ordering here of the subproblems that we are going to use? So there's one thing that is obvious, that if we are computing for I comma w, then we are only going for I minus 1, right? So if we compute opt of I comma whatever w before opt of j comma w for I less than j, then we are good. So that gives you one ordering. But what about these w's itself, right? So what does now I comma w use? It also uses, like, the one row before. So this is fine. So that gives you an ordering. It does not use anything from the same row. And we also need some initial condition, right, to initialize this. So initially, or what we can define is, of course, opt of I comma 0 is equal to 0 for all I, right? Because if you have zero capacity, then of course you cannot get any this thing. And actually, we want something more also. Opt of 0 comma, because this is our going to be our induction, right? So if you don't have any requests, of course you can't fill anything. So opt of 0 comma w is equal to 0 for all w. But there is one thing that we have not really looked at. That is that how do we get these w's? What are these w's going to be? We had some capital W, and now we are saying that okay, these w's we want to get these for these small w's. For I, this is fine. So this I is 0 less than I less than n. So the range of I is like very clearly defined. But what about W? If the capital W is not an integer, then we are in trouble. W and Wi's are not integers. Then we don't really know that how to get from, like, this capital W to Wi's and so on, right? I mean, we'll have to do more work for that, because then we have to look at every possible, reduction in the capacity and so on. That can be done. But, like, just for sake of convenience, for now, let's assume that W and Wi's are integers, which then can give us an ordering or range for W also, which is again 0 less than W less than equal to capital, right? So we assume the total capacity to be integers, and we assume all the weights to be integers. Okay. So this is fine now. And now this table is very well defined. This opt of I comma W, right? This is an W times n size table, right? Okay. So why am I saying table? Because now we want to design an algorithm, right? So basically computes opt of I comma W using the recurrence. And like we said in the last lecture, now this time we are not going to, like, recurse, but we are going from bottom up. And now this is a two-dimensional table instead of one-dimensional table. Okay, good. So now we are there, right? So, and also there is just one thing, that from this recurrence, okay, let me just copy this. All right. So now we have this recurrence, and now what do we want to say? We also want to make a decision about whether I belongs to the opt or not. Right? Oh, this will not work. This is strange. Oh, either the whole image will go or not. Okay, fine. Let's see. So from this we want to. So this is like some recurrence in the book. Whatever, let's say 6.8, so that in the algorithm we can refer to it correctly. Okay, and from this we can also determine that I belongs to whatever the optimum solution. For 1 to I, right? If and W, if weight of I is less than or equal to the weight, and this quantity, the first quantity is, no, the second quantity is greater than or equal to the first quantity. That is Wi plus opt of I minus 1, comma, W minus Wi is greater than or equal to opt of I minus 1, comma, W, right? So if that happens, then we can say that I belongs to optimum solution. And this, if we have the table for opt, then just like before, we can figure it out. That for each I, we go for these numbers and then we figure it out. So that is not going to be very hard. So why is this so much down here? Okay, so let's look at the algorithm now. Will the algorithm fit? Yeah, I think it can fit. Let's make it okay, so this is the algorithm, right? So what does the algorithm say? That now we have an array, now we have a two-dimensional array, now we don't have just a one-dimensional array. So this is a two-dimensional array. Of size, let's say n plus 1 times w plus 1, right? So let's say, you have this array now, or you have this table, and here you have 0 to n, and on this side you have 0 to w, and you have these cells. And final answer is here. Good. So now what do we say? First, of course, we have filled these with zeros so that the first row is clear. We can also fill these with zeros if you want. Okay, good. Now for every ith row, we want to fill this, assuming that we have filled the I minus 1 rows. So again, by induction, we are working here, or we are showing the induction. So now for I is equal to 1 to n, we go from bottom to up. And for left to right, for w is equal to 0 to w, we fill the entries. So we look at any entry here. Suppose this is I comma w. So suppose this is the ith row and this is the small w. And for this, what do we use? We use only the entries of I minus 1th rows, right? We don't use any entry of ith row or above. So, and by the time we reach the ith row, all this is filled, right? So we can find the values. What are the values that we need? Opt I minus 1 comma w, which is the right one, the one right below this. And then we need opt of I minus 1 comma w minus wi, which is going to be somewhere on the left. Let's say this one. And using these two and taking the max of these, we can fill I comma W, provided this I is, I mean, yeah, even if this Wi is greater than W, right? If this Wi is greater than W, then of course we don't include it. So anyway, then we use the recurrence to fill this entry up, and then you just keep doing this for every row and every column, which is W, and finally you reach here and you return the final answer, right? So is there any question about the algorithm?
But in the algorithm, I comma 0 is not initialized, means what's written in the algorithm.
It doesn't really matter actually. I mean, even if you don't, I comma 0, it's initialized in the opposite direction. You are right. So also M of, yeah. No, this is fine, right? This is the only thing that you need actually. I mean, you don't need. I had initialized that, but you don't need this initialization actually. You just need need to go row by row, and that is enough, right? Is that okay? Because what are we doing in the recurrence? We for any row I, we are using the values of rows below I, and that's all that we need. We don't really need that. Okay, column 0 has been initialized. Does that answer?
Yes, sir.
Okay, Rishabh. Good. Thank you. So this is now the algorithm should be clear, I guess. And I mean, of course, let's do a quick analysis. And as I said, correctness first, and correctness follows by induction on I. I is equal to 0, be easy, like base case. And now suppose I is equal to I, like I is equal to K, we want to find something. Or let's say till I it has been computed. So suppose we want to compute opt of I comma W by and the algorithm has already computed opt of I minus 1 comma W for all, or W prime, let's say, for all for I, okay, yeah, there is no for all W prime actually, for all W prime 0 less than or equal to W. So now we can compute opt of I comma W using the recurrence, correctly using the recurrence. And why correctly? Because by induction hypothesis, this is correct. That for the smaller i's, this is correct. Okay, good. So this is the correctness, and this is not very hard. And what else? Yeah, running time. So for each I and W, how much time does it take? For a fixed I and fixed W, how much time computing the recurrence take?
Order 1.
Order 1 time, right? So for fixed I and W, opt I W takes order 1 time. So total time is proportional to size of the table. which is order
n times w.
n times w, right? But this is not exactly polynomial in n, right? Which is our input size. It depends on w also. And is polynomial in w. Which is the biggest number, like, if you sum these numbers up. So this kind of algorithm is called pseudo polynomial time algorithm. It is not exactly polynomial. Why? Because the w that we are getting is not, does not really represent the size of the input. And this is actually, so, this algorithm will work well for small w, but for large, it can be bad. So always, like, have this thing in mind whenever you are doing these DP sort of thing on weighted things, that it is not exactly a polynomial time algorithm, but this is, something which is slightly different. It's called a pseudo polynomial. Good. So this is like, this is the problem. There is another related, actually, maybe more famous problem, but now, like, we have done all the hard work to, solve that, like, pretty easily, I would say. So that is the knapsack problem. And what is the knapsack problem? That now we are given, so we are given n items, 1 to n, right? Their weights, W1, W2 to, let's say, Wn, right? And their value, which is, can be different from weights, V1, V2, Vn, right? And now we are given a bag with capacity, let's say again C, right? And now we want to fill the bag weight capacity, right? And we want to fill the bag with maximum value. So this is a very natural problem, right? That you have a capacity of the bag, but you don't want to choose some arbitrary things. You don't want to choose things which are cheap. You want to fill it with things which are, expensive, or, which are costly. So which have large value, right? So you want to maximize your value. So how do we formulate this now? So we want to find a subset, of course, of items. That maximizes something. What? That maximizes what? Anyone?
Total value.
Sigma vi.
Sum of vi, total value, right? So I belongs to S. Sum of vi is subject to
Sigma wi less than equal to c.
right. So this is the formulation of the problem. So this is like, this might seem that, okay, this is very different, and, now we are not really maximizing the weight that is there. Now we are maximizing the value that is there. But if you look at it now, like, this is very, like, actually, if you try to write the recurrences now, so again, it's the same thing, that you have this bag, and so suppose you put, okay, let's start with the nth thing, right? So you want to fill this up, whatever. Now you want this nth. So let's optimum solution. N does not belong to O. So what is going to be opt of n comma W? Tell me. If n does not belong to the optimum solution, then what is opt of n comma W? So again, we want to do it. Again, we want to, the subproblems are going to be the same, right? Because the capacity is going to decrease. So we want opt of n comma W, because now if we put W inside, so here it does not matter. This is going to be n minus 1 comma W, right? like last time. But if n belongs to O in the optimum solution, then opt of n comma w, what do we get? Opt of,
B.
yeah? Tell.
Opt of n minus 1 comma w minus wi plus vi.
Wn plus
Wn.
w, right?
Vn.
Yeah, plus vn. Sorry, thank you. Right? So this is what is the value that we are getting now. It's just that here instead of wn, here the opt will use the value which is vn. But still the capacity decreases by wn only, right? So that is why the sub problems will be of the form opt of I comma w, right? So let's just write the recurrence again using for this general problem. And what is going to be the recurrence if w is less than wi? Again, that is like, then of course, it cannot be opt of I comma w is equal to opt of I minus 1 comma w. So this is just, sort of sanity check that if the weight is more than w, then of course we cannot put it. And otherwise, opt of I comma w. Can somebody tell me while I'm writing it? Max of, can somebody speak while I write?
Opt of I minus 1 comma w
Yes.
comma opt of I minus 1 comma w minus wi plus vi.
Wi plus vi, right? And that's it. And this is the recurrence, because it's just that now we need to add the value instead of the capacity to get to the opt, right? That's it. And the algorithm is very similar to now subset sum. In fact, like the only line that will change in the algorithm is just this line. Use some other recurrence to compute m of I comma w, and everything else remains the same. And in the recurrence also, what changes? Just here you get a vi instead of wi. Nothing else changes, right? And so, what is going to be the running time of this? Again, order
WN.
and yeah, and comma and times w. Right? So this is what So knapsack. So generally, like in some courses or whatever, they motivate or they do the knapsack thing. But I also like this treatment of the way the book does that. First, it goes through subset sum where the variable is the same, and then still you need to add one more variable, and then it goes to knapsack where actually you can just see the small change, and that works. So I like this approach also, because directly knapsack can be that, okay, you want to maximize the value, but the capacity decreases and so on. But once you realize that what the subproblem is going to be, and the subproblem is going to be for a particular, subset and a weight. And when you have that, then you can see that, okay, now if I have these subproblems, how do I calculate or build up for larger subproblems? And that becomes very easy. That now again, you just, look at the matrix entries or the table entries. And again, you have filled the lower tables, and any entry you see, you have to look at the one below and maybe something to the left, maybe here or here or whatever. So that is all there is, right, about these two problems. But the main part here was that the obvious subproblems, which is just like taking a subset or reducing one guy, might not be enough. You might need to add one more variable, right? Any questions?
Sorry, we could be saving space by using a 1D table as well, right? Like, given we are only concerned with values of one row above and not the entire table above,
Oh,
would
yeah.
just be storing the values in one row above.
Yeah. That is, you can override sort of you're saying, right?
Yeah.
Yeah. We are not optimizing space. Yeah, we did not optimize for space. You're right. You can just keep building and keep forgetting the older values. Yes, you're right. I mean, at one time you might need to still keep two, like rows, but yeah, you can do it with like order W space.
Sir, I had also seen another version of such a solution when W was quite large and the sum of the VI's was not so large. So in that case, they had considered a subproblem such that opt of I comma C is the minimum weight required to get a cost at least C in the indices 1 to I. Uh, uh,
Minimum weight required. Okay. Okay.
Basically, C is now the cost is now the variable and W
Yeah,
is the optimal answer.
yeah, I understand that. Yes, and then you can build up using that. So then your running time will be n times C,
N
right?
times, yeah, N
Yeah.
times sigma W.
Yeah. Yeah. Okay. Yeah, that's a good one. I mean, yeah, if you want to, like, if you want to help others, maybe you can put the source or something in the chat or even on Piazza, and I think it will be nice for others to look at that as well. Ayush. Okay.
Okay. Okay.
Okay. Any other comments, questions, anything? Okay, good. If not, then thank you for coming and see you guys tomorrow. Okay. Thank you.